the meeting. So it's one thing to kind of, see them in the meeting and have to comment on them right off the bat. And it's another thing to kind of sit down and study them. So it's more efficient for me and probably for you to send the reports and then we can kind of, uh, discuss them in the meeting. And when you send the report, make a note that you need to explain things pretty well. And putting them in a document that you need to explain them will make it a lot easier for you when you finalize the project and you want to kind of write your paper on it, right? You can kind of use everything that you've reported to me as a point of reference and also as a kind of building block for your final paper for the project.
Sounds very good, Professor.
Yeah, so just remember to explain things. So right now I'm guessing, I haven't seen it, but I'm guessing your document will mostly be something that you can show results to me as you explain. Remember, when you send it to me through email, then you're not there to explain it to me. So
Hmm.
all the explanation needs to be typed in.
No problem, Professor. I got you.
Okay. So let's
So,
see what you've done.
sure, yeah. I want to share my screen. 1 second. So I just want to quickly remind you about what we went over last meeting. So
Sure.
essentially, we are building two models. Um, do you remember what alpha is and what beta is and that
Hmm.
stuff, Professor? So
Yes,
the
I do. I think alpha was the transition probability for going from
Mm,
a susceptible state to a infected state, and beta was going from um, did you have
refractory state to
recovery
the
state as well? What was your
yeah.
model? Three state or four states?
Three stages.
Three
So
stages. Okay.
silence, firing, refractory, and silence.
Okay.
Alpha is silence to firing, and beta is refractory to silence. But always, when it's firing, always it goes to the refractory state next step.
Okay, good.
So I have built two models, and the first model is exploring the effect of alpha and beta.
Nice.
Hmm.
Okay.
And this model, so this is how I define alpha. We know that each neuron has, let's say, 200 neurons, right? And each of its firing neighboring neurons will trigger alpha. For example, I have 10 firing neighboring neurons. And for the first one, I roll a dice, and if it fails, I move on to the second one. And if it fails, I move on to the third one, such that if at least one of my neighboring firing neuron succeeds in determining alpha, I will fire at the next time step. So I think that's kind of a realistic representation to the real world brain model, right? Because if one of your neighboring neurons successfully triggers you, you will fire, even though maybe 99% of your other neighboring neurons fail to trigger you.
Um, that's true, Vincent, but the way you should probably think about it and also implement it is by, so let's say, as you said, there are 10, um,
Firing neighboring neurons.
right, there's 10 firing neighboring neurons. You should, um, you should calculate the probability that, let's see, I'm thinking about this as we go. So you should do each one of them. Yes, that's true.
Hmm.
One by one. That's what you're doing. and then you're stopping it when you get to a point where one of them actually does send a signal.
Yeah,
Okay, so I'm just thinking you should go through the booking first and then apply. Is there any difference? I guess there's no difference. Okay, good. Yeah.
sounds good.
But
Hmm.
yeah, so just to make sure you're not, when one of them actualizes that probability, meaning that it does send a signal and causes the neighbor to fire, you stop kind of rolling the dice after that.
Yeah,
By
yeah, yeah,
rolling
yeah.
the dice, I
That's
mean,
what yeah, that's what I explicitly meet in my code. I make
okay,
sure that is already met. Yeah.
okay.
And also, I want to explain that, let's see. So for this project, last meeting you mentioned that we start with a small n, 20,000. And here's an average number of connection, k equals to 200.
So hold on,
However,
just to make sure, I'm not really seeing anything on my end.
oh, you're not
All
seeing
I'm
my.
seeing is just name of four files. It says effects report,
Oh my
effects
God,
report.
I am terribly sorry, Professor.
Okay, now it's better.
So yeah. Um, so I want to explain two basic rules that are applied for both models because I've done two models according to our last meeting. We kind of explore what the different two models does. So these two models have two fundamental rules. First, the total neurons are the number of total neurons is said to be 20,000. And I actually test how quickly my computer runs because my computer has a really good graphic card and really good CPU. So, and also I optimized my codes for my specifications, so it runs code really, really efficiently. So
Mhm.
I believe that there's really no need for me to run on clouds unless the N goes up to very, very high. I think my computer can already satisfy that. So N equals to 20,000 for both models. And the average connection number, meaning how many other neurons are connected to one neuron, is 200. However, here's something that you pointed out last week, last meeting, Professor. The actual connection probability is k over n. So we know that n equals to 20,000 and k, as we just mentioned, equals to 200. So the average connection probability is 1%. However, since it's probabilistic, one neuron may connect to more than 1% or less than 1%, but on average, the percentage is 1%. That is a point that you explicitly mentions
Mhm.
last meeting. I just want to point it out to you, Professor.
Right, that's good. Thank you for that. But can you also tell me how you determine that probability? How do you make one neuron be, let's say, to connected to 150, the other one is connected to 200, the other one is connected to 235 or something like that?
Well,
How do you decide their variability?
variability. I just roll dice. So here's the thing. At the beginning of the simulation, I generate multiple seeds of adjacency matrix, right? And because the experiment need to be reproducible, meaning that if I run a different computer, I need to get the same result. So I save the adjacency matrix. So when I'm generating, like I'm using a random number generator, um, but after I generate that, I save that pattern such that if I run the same program on a different computer, I will use that pattern. So I don't need to generate a different adjacency matrix such that the experiment will always get the same result. And does that kind of make sense, Professor?
Mm-hmm. Yes. Okay.
Does that answer your question? And
Yes.
really
Yes, it does. Thank you.
sounds good. Sounds good. Yeah. So this is my first
Okay, so
model.
wait, hold on. I still haven't understood the difference between Model A and Model
Oh,
B.
no problem. Yeah, I'm just about to explain it. So for model B, it's still the same connection probability rule, K over N. Still the total N to be 20,000. However, we don't use alpha here. Here's the mathematical equation representing alpha here. It is the numbers of firing neighboring neurons over K. Over K, yes. So for example, if I am connected to 200 neurons, my denominator will be 200, and out of my 200 neighboring neurons, 167 of them are firing. My alpha in this case is 167 over 200.
Uh, that's hmm. So that's a different
That's very,
model that you are
yeah, yeah,
exploring
yeah.
because your model is supposed to have the models are supposed to have a fixed alpha, right? That's
That's
just a
model one,
threshold
right?
for firing. So it's like, I don't know, let's say 1%, 2% or something like that. And you keep that fixed throughout your simulations. And I guess that was your model A and your model B is different.
Yeah. So think about it. The probability is not static, it's actually dynamic because your numerator, the number of your firing neighboring neurons is constantly changing. I think it's actually more interesting to explore as
That parameter already exists in model A. That's just the you know, it's the
uh
fraction of, so the parameter you just mentioned is a fraction of active neighbors.
yeah,
Yes.
yeah.
Neighbors that are kind of firing. And it's their fraction. It's how many out of the total neighbors that are firing. So that just gives you the local activity. And then you're supposed to compare that fraction with the fixed probability, essentially. I don't understand how that could be determined as a. So maybe you could tell me in your model B, what are you doing? So let's say,
So okay,
there's 200 neighbors, and at this particular instant, for this particular neighbor, let's say, I don't know, 75 of them are firing. Then what do you do? So it's 75 out of 200.
so my at the next step, my probability of being fired again, my probability of being fired is 75%. So that means it's not really affected by one neuron. It is a
So the probability of
so
being
here's what
fired is 75%, and
so
then
yeah, so here's how I would approach this. If you get think about like the more people persuading you, the more likely you're prone to believe something. And in model A, it's that if one person successfully persuades you, you're persuaded. But here, you're very less likely to be persuaded if only one person persuades you. Yeah, you got what I'm saying, Professor.
I do understand that's true, but that also exists in the first model, right? So in the first model, uh, the fixed probability one, the
Hmm.
more neighbors are firing, the more your chances of firing yourself.
Yeah, but that one is already very high. for example, yeah, I agree with what you're saying, but Model 1 has a much higher firing percentage compared to Model 2. So yeah, they are
It just
to
depends on what you choose your alpha to be, right? If you choose your alpha to be 1 out of 1,000, then very few neurons will fire. If you choose it depends on what your average neighbor number is. If your average neighbor number is 200, then
it's
obviously
very yeah.
if you choose something like 2 or 3%, then the model always fires, right?
Actually, you know what, Professor? Even at 0.1%, it still fires, never dies out. That's what my data shows. So yeah,
0.1,
alpha, even at that
that's a huge
percentage.
alpha.
No, no, no,
10%?
no, 0.1%.
Oh, zero, like 1 out of 1,000
Thousand.
or 1 out of 10,000.
1/1,000.
Yeah, if it's 1/1,000 and then on the average you have 200 neighbors, it
Yeah, it's
should
still
not always
fire.
fire.
Maybe that's too much. Wait, let's see. Actually, 0.01. No, no, hold on. Well,
So let me just
no,
make
no,
sure
I am very,
the models, and then
I'm
we
very
can go
sorry.
through it, and maybe it's too early to judge. I'll look at the results and
No,
then
I'm
we can
so
judge.
sorry. It's starting on 1%. I'm very sorry. It's 1% to 10%. It's not,
Yeah, if it's 1% and you have 200 neighbors, essentially, you're always going to be firing. But if it's
yeah.
1,000th of a person, 1,000, 1 in 1,000, then that should not happen. So
Okay.
just to make sure, in the Model A, you're going to um, flip a coin or call the random number generator every time for every firing neighbor to see whether they activate the neighboring site. In Model B, what you're going to do is you're going to calculate the local probability at that particular time, depending on what fraction of neighbors are firing. And then whatever that fraction is, you're going to say, that's the probability with which I'm going to fire. Then you call a random number generator with that probability and determine whether something is firing or not.
Professor, you're framing it precisely and accurately. Yeah, exactly.
Okay.
And
Uh,
yeah,
I
and
think that's an
also, mhm.
interesting way of looking at it. Let's see what the results are.
Sure, but I still want to point out two things. So what are we exploring? Like, what are we trying to find? So essentially, we're trying to find what each parameter does. In Model A, it's alpha and beta. But in Model B, as you mentioned, it's a fraction of the firing neighboring neurons. But how could, at t equals to 0, when there's no neurons firing already, the fraction will constantly be 0. So the system never even starts. So at t equals to 0, we give a percentage of firing neurons. So for example, so our n is 20,000, and if that percentage is 1%, then 200 neurons are already fired at t equals to 0. So we're giving it an initial firing neuron number. So for number two, the parameter we are looking for are two things. First, beta, obviously. Second, that initial firing neurons percentage. These are the two parameters we're exploring in Model 2. Sounds good?
Okay.
And
Yeah.
also, um, I did some research that when we have two independent variables, we can use two methods to determine the effect of each parameter. The first one is one at a time. I think it's OTAT or something like that, right? So you're keeping the other constant and you're changing one independent variable. For example, because there are two variables, alpha and beta in Model 1. So we, for example, keep alpha at 1%, and we change beta from 1% to 10% to 20%, things like that. So that's the high school method of researching, keeping one independent variable, changing
Mm-hmm.
the other to all the rest constant. The other one
Sure.
is called it's called factorial method. So we're changing two independent variables at the same time. However, mathematicians proved that not only this method preserves the individuality of each parameter, meaning we can cancel out the effect of the other factor, but also we will be able to find something that the first method, keeping only one independent variable changing, cannot provide. That is the interaction between two independent variables. For example, alpha might have an overall, for example, increasing effect for the amplitude. However, when beta is high, alpha may have a magnifying effect compared to that when beta is low, meaning that these two independent variables could interact with each other. Does that kind of make sense, Professor?
Unfortunately, it does not. I don't see how you're going to get anything extra by doing the second method. The first method just maps out, since these things are independent variables, um, you are keeping one constant and changing the other one. You're mapping out how the change of the beta, for example, affects the system while alpha is constant. And then you're doing it the other way around, keeping beta constant and changing alpha. You should, by this method, be able to map out all the behavior of the system. There's no need to do any other method. I don't see that
Yeah.
unless they're not independent variables. I think that second method comes into effect when you talk about them being not independent and dependent variables, and then you might want to kind of change two at the same time.
Well, I
So,
mean, yeah. Yeah, essentially, yeah, if you map out everything using the first method, you're essentially doing the second method because you get all the coordinate. For example, looking at this graph, you already get alpha and beta as the x-axis and the y-axis. So, for example, if we keep alpha constant at 0.01 and we're changing beta, yeah, you're essentially doing the same thing. I get what you mean, Professor. Yeah.
mhm.
But I
So,
did both method at the same time. So yeah, even though the second method seems useless, we can also look at the data provided by the first method. So yeah.
okay. So, let's go through your results. You have a heat map, I see,
hmm
and you have a model A
So,
and amplitude. So, is amplitude the number of firing
neurons. Yeah.
on the average? Because the number of firing changes with time, yes? So what time are we
Yeah.
looking at?
So the model has a transient stage. So we're looking at the oscillatory stage.
Hmm.
And as you mentioned before, even though it ends the transient stage, it still needs some time to reach the oscillatory stage, meaning that in between there's a stage called steady stage. It doesn't really fluctuate that much, but it doesn't show a pattern that repeats itself. So I designed an algorithm detecting when it reaches the oscillatory stage, and that's when we are looking at the amplitude.
Okay, so question first. Does it always reach an oscillatory state?
Nope. Nope. Some of them doesn't.
Okay. When they don't reach an oscillatory state, what kind of state do they reach?
They reach a stable stage, meaning the pattern is irregular, but it's
Okay,
not
but
like
it's still
transient
going up
stage.
and down and fluctuating with time, but it's irregular.
It's irregular, yes.
Okay.
So maybe you can see right here the black one. So
So hold
that's
on. So what I'm seeing here is the average of that irregular behavior or the average of the oscillation? Because, when
The
you have
average of
oscillations or irregular behavior, they're not a constant number as a function of time. So you're giving me a constant number. You're giving me something like 200 or 250 or something like that for each square.
yeah, that's the uh that's the amplitude of
Right. So I'm asking whether the amplitude is, so the
it's
amplitude is not a constant number, right? Are
oh, it's
you
average. Yeah, I
average
see your
over
point.
time?
Average over time. Yeah.
Okay. So
Yeah,
if
because
it's, for
yeah,
example,
it's
oscillating
mean
back
amplitude.
up and
Yeah,
down, you're taking the average in the middle.
right. Yeah,
Yes.
precisely,
And if it's
professor. Yeah.
fluctuating in a kind of random way, you're still averaging it over time.
Yeah, exactly.
Okay. And that average over time needs to be long, right?
Yeah, very
That's
long. Yeah. Yeah.
okay.
And
Okay,
this
so
is
let me now hold on,
uh,
go back to the first one. Let me make sure I understand what this is model A, and you are finding that you almost always have activity in the system, even if your alpha and beta are very small, you are not seeing that much of a change. Um, Once your alpha is small and your beta keeps increasing, which means for low alpha, alpha is driving the system and beta doesn't make a whole lot of difference.
oh, if you're looking for the data summary, I actually include that in the report later. But you can also interpret the data by yourself, professor, however you want.
Okay, so you have interpreted these results?
Yep.
Okay,
Do you want to look at the second graph?
yes, go ahead.
So this is the mean activity. So that's not a percent, but the that's not amplitude because amplitude is the fluctuation part, right? So it shows the change from the baseline, and that one just shows the number.
Okay, so the difference between the previous data and the current data is the last one was,
The
no, I
last one
don't
was the
understand.
so amplitude is the change from the baseline. For example,
Oh, I see the change
my
from the baseline. Okay,
yeah,
okay.
that one's just the actual number. So
That's
yeah,
the baseline. The second one is the baseline.
yeah,
Okay.
and
So you have very large
very large
this
number
in
firing
this
when
in this brain there's a at any given time there's huge parts of it that are active, right? So your system was what, 20,000? So
hmm.
yeah, big portions of the brain are at any given time active. Okay.
And here's some summary about the effect of alpha. So when we keep beta constant at zero point 0.5, we can notice that as alpha increases from 1% to 10%, the mean number of neurons firing increases by 176. And it's monotonically increasing, meaning that it's strictly increasing. It always increases.
Um, what is 28.32.2 plus minus 1.3? What is that number signifying? Two.
So that's
Oh, I see.
the,
So these are the mean activities that are increasing as a function of increasing alpha.
you're saying precisely, Professor. Yeah.
Okay.
So, yeah. And
So you should, okay, so then you're, okay, so you're slicing through point 0.5 beta. Okay, that's good.
yeah. And also the amplitude changes by 3.35%. That's a large number. But also, I would explain what non-monotonic mean. That means that we are increasing alpha amplitude is not always changing. Sometimes it dips down. However, the overall trend is increasing for some reason. Yeah. So
Hmm.
that's just something to notice because I cannot say that increasing alpha always increases amplitude. That's just inaccurate because that's not what my data shows me. So I just marked that down.
Okay, that's interesting. So the average is always increasing, but the amplitude is not necessarily getting larger. The baseline is getting larger, but the uh, the actual fluctuations are not getting larger. Is that
Yeah,
what you're saying?
professor. Yeah.
Okay, that's
And
interesting.
the period, so when alpha equals to 1%, beta equals to 5%, the pattern doesn't repeat itself. So there's no period because there's no oscillatory stage. And when alpha equals to 1%, 10%, beta equals to 5%, there's also no oscillatory stage. So
Hold on a
I
second.
don't,
Let me digest that a little bit. So between alpha equal to zero point 0.1,
oh, I don't know what that is. Sorry. Oh,
0.01.
I'm so sorry. I want to explain that again. I want to explain that again.
Okay.
So when alpha equals to 1%, beta equals to 5%, it never reaches the oscillatory stage. So the pattern is not transient, but it's also not regular. It doesn't repeat itself. So that's why the period equals to 0.
Okay. It's just some random events, or is
Random
it that
event. Yes.
right? The
But
system is
when
still alive and there's reverberations and there's transients, there's things happening in the system,
hmm
right? But
Yeah,
they're
yeah.
happening in a random way.
Yeah. But when t equals to no, I'm sorry, when alpha equals to 10%, beta equals to 5%, the period is 4. Every 4 steps, the pattern repeats itself.
Every four, that's pretty small
Uh,
period.
I would double check that again. I think that's way too small. I'll run the code again and let it analyze the pattern again and maybe I'll keep an eye on that one, Professor.
Okay, so one thing to since it's been a long time, our last discussion, I don't remember whether I emphasized this. I'm sure I've mentioned it, but I don't know whether I've emphasized it or not. One of the things that are the that should be the outcome of your studies is when, in terms of what parameter regime, you see clean oscillatory behavior and when you don't. This is much of interest to us, right? So
So
it's
you're
it's good
saying
that you've studied this part, but it's we want to kind of have a better understanding of uh how generic how generic is the oscillatory behavior. Is it just for a fine parameter regime around alpha or beta, or does it happen for a wide spectrum of alpha and beta?
I think uh oh, I didn't have that one, but I will. Oh, it's very simple. I can do
Right.
that
So a
later.
prerequisite for doing that is to make sure that you have a very good definition of what a oscillatory behavior is, and you have a very solid way of measuring it systematically, including measuring the period. Right.
Sounds good, Professor. I'll add a feature very soon. Sure.
Okay.
And and it never this model never dies out because even alpha is very low as long as so it because it's individually triggered, right? So even alpha is very low. The total chance of being fired is also goes up to very high. So at the
No, I
lowest,
understand. That's pretty
yeah.
obvious to me, and the reason
hmm
for that is simply because 1% is not necessarily a low alpha, right? It sounds to you and me that 1% is low, but it's not really low. You could drive it much lower than that. So what is low and what is high in these models are kind of dependent on what your K value is, right? So if your K value is um, well, it depends on what what your K value is. So if you have 200 neighbors on the average, eh, an average of an alpha of 1% means on the average two of those, if only two of those fire, you're going to fire,
Yeah, yeah, yeah,
which
yeah.
is not very hard to realize, right?
Yeah, yeah, yeah.
You could totally have just, a very kind of a not active brain still having 2 out of 200 neighbors firing, which means on the average, you're always going to be kind of reverberating and going through activities and never going to a silent state.
Yeah,
Um,
yeah.
so you do want to kind of explore lower values of alpha as well.
Like lower than 1%, right?
Absolutely, yeah. There's
I
no
got
need
you,
to
Professor.
stay into two significant digits. You could go to a 0.5%, one out of 1,000, 2 out of 1,000.
Don't worry about it, Professor. Yeah, I'll know it. Yeah. So for the sake
So
of
you
time,
your
uh,
baseline, just to get a point across, your baseline for alpha and beta
mhm.
should be where you actually see only transients. That's where you should start off from. You should have an alpha, you should have a good understanding of what it means for a given alpha and beta within my model, where I'm going to see some activity and then all the activity is going to die out and the brain is just going to be dead, right?
I
That's where
got
you
you.
get a base idea of, okay, this is not the interesting stuff. Let me see where I work out to start getting some interesting stuff. And then it seems like most of the simulation you have is in the regime where there's a lot of interesting stuff going on, meaning that there's a lot of activity going on, and that's not necessarily corresponding to what the actual brain is doing. So brain is always on the verge, you know? This is what I kind of study as somebody who's done
Yeah,
simulation
actually,
of the
I found
model.
your paper on Nature, Professor. Like when I was
Okay,
researching how to do the simulation, I found your paper. It's very inspiring and very good.
thank you.
Yeah.
Yeah, so
And
so we want
mhm.
to be kind of one of the things that's important. You probably saw a keyword in bunch of papers I've written more than one or two papers on this topic. One of the themes that are true in my papers is what I call criticality.
Oh
And
yeah, I read that paper. Yeah. The
okay, so the criticality
subcritical
idea of the
critical.
brain is that brain is always on the edge. It's not
Hmm.
too active and it's not quite silent, but it's right there in between. So it's kind
Interesting.
of going, it's fluctuating, going up and down, but it's not necessarily doing anything kind of regular because that's too predictable. And it's not doing anything kind of boring like being silent. It's kind of active, but active in a good balance between being predictable and also unpredictable. So
Well,
too much
interesting.
activity, not too little activity is where a real brain is. That's not necessarily where we want to go right now. We want to map out all the behavior in your model. And then eventually, once we understand everything about the model and we kind of hone it down to a given particular situation, then we can kind of study the whole concept of criticality as well, perhaps.
Sounds very good, Professor.
Okay.
So for the sake of time, actually, at different slices of beta, alpha shows similar effect on the graph. So I'm just going to skip that. I include a summary of alpha's effect at the end of my report. And let's look at the effect of beta. Uh, they all follow a similar trend. So I only take one slice. When alpha equals to 5%, we notice that the mean activity increases as beta increases. The amplitude increases, but not very significantly. It increases by 1.49. And the period interest, let's see, the period here from 0 increases to 14.
Very good. Yeah. So my gut feeling was that period should strongly depend on beta.
So it's actually in the summary, but yeah, I my research found that when beta is larger, you get a larger period. That
Hmm.
sounds very counterintuitive, but yeah,
So when beta is larger, you're kind of transitioning faster. Yes, you're right. It's counterintuitive.
no. When beta is larger, the period got larger, meaning that
Longer time.
it takes longer time.
And
Um,
that's counterintuitive because beta being larger kind of shortens the waiting period and gets you ready quicker.
yeah, that's very counterintuitive, but yeah,
So your beta is, hold on a second, one more time. What you have observed is that larger beta shows
larger
larger T, larger
larger
period.
period. Yeah, yeah. And yeah, that's model that's model
But
A.
hold
Yeah.
on. So this kind of because we were a little bit curious about how you define period in the previous result that you just showed me too, right? You had like a kind of a short period for something, and yeah, that was a so you might want to one of the things that I said in your previously in your results is that you need to kind of have a very good and systematic way of measuring a
Defining
period. And I wonder whether this is an artifact of not being very careful about the measuring
definition of it.
period because it is very counterintuitive, and the more I think about it is the more I'm trying to convince myself, or I seem to be able to convince myself that it should be the other way around.
Gotcha. I will.
Yeah.
Yeah.
So
Um.
beta is essentially what we call a frequency.
Yeah.
Both alpha and beta are frequencies in a way, and frequency is always inversely proportional to period.
Yeah.
So double make sure of that.
Yeah. I will double run it again and see.
Okay.
'Cause, yeah. I see why that sounds very weird. So
Yeah.
that's
I'm glad that
model
you
one.
had the good intuition about this behavior.
Yeah. So model two actually every single trial it dies out.
Huh.
Yeah. Even though you have a very high initial um firing percentage. So under this case, 20%. That means 4,000 neurons are firing initially. It still dies out. And not to mention that when this percentage gets smaller, it also dies out. It also dies out. So
Hold on.
all of them,
How do you report that that number changes everywhere and every time? How can you use that number as a parameter to show your results against? Do you know what I mean? So your alpha, if I understand, maybe you've called it F0 because it's really not alpha anymore. But that number that I understand is on your horizontal axis in this figure is the fraction of active sites to total neighbors. Yes?
yeah. Actually, the denominator is not a is actually a constant. So each neuron,
Sure. So
the
the denominator
yeah
is, let's say, 200 in your model.
yeah
Okay? But
yeah
the numerator is changing from neighbor to neighbor and also from time to time. Excuse me. Even
yeah,
for a
but
given
yeah
neighbor.
I see your point, but yeah, but
So how do you characterize that?
so
What does it
that's
mean for me to even ask what's the behavior?
that's like the initial numbers of firing neurons. So initial at t equals to zero, we give it
Oh,
f zero.
F0 is the
Is
fraction with which. Okay.
remember, yeah, because remember when t equals to zero, if the numerator is zero, the system never
Okay,
really
so
starts.
F0 is not your, okay. So your F0 is the fraction of initially active neurons.
Yeah.
Okay, I misunderstood. Okay.
No problem, professor. So yeah, all
Um,
dies out. No interesting stuff. But I can show you
so do you
which,
have an understanding of why that happens?
yeah, um, because the let me think about so it kind of behaves like this. The number is getting smaller and smaller and smaller because firing neighboring neurons is essentially always smaller than n, right? Even though some of them may be very lucky, for example, it has 210 and also 210 of its all of its neighboring firing neurons are firing. That's very, very low chance. So the probability is always smaller than one, so that number gets smaller and smaller and smaller and eventually dies out.
Exactly. So the probability of activity in your model is biased towards getting smaller and smaller and smaller, eventually dying out. Very true. Very good.
Yeah, but also, we can, yeah, even though it all dies out, the number, like the extinction, I call it extinction time. So at certain parameter, it dies out sooner or later.
Sure.
So that's what I kind of found.
Right. So hold
Uh,
on. Go back up again. Go back up again.
sure.
Right. This figure. So one thing that you can kind of make sure that you understand, and these things are always good to ask questions to deepen your understanding of what it is that you're dealing with. That's like a sign of being a good scientist. You would expect the model to die out later and later, the bigger your initial firing fraction is, which is consistent with what you're saying, essentially.
Well, not really, Professor. It's actually not like as F0 gets larger, it dies out. It
For a
actually, like,
second,
right.
yeah, you're right. It's not that way. Wow.
Yes.
It's actually random. That's what you would expect, that if you started from a larger initial firing set, then it would take longer to die out because you have to kind of take more time to decrease and decrease and decrease. Therefore, you would have more time to go to a zero state, but you're not really seeing that. Um,
It's probably some noise, I guess. Because essentially the model is probabilistic. So should I run like multiple experiments at the same points? So for example, 0.11, 0.8, that point, I run 10 trials and I take the average such that the probabilistic effect is minimalized. So that way it can give a more precise understanding.
well, I mean, the model is generically not that interesting because it seems to run into a, not active state, and we know that's not biologically relevant. We're trying to find, we're trying to discuss models that stay active and then talk about that activity, whether that activity is small or large, whether it's periodic or random or things like that. So if it's kind of always going to a non-active state, sure, you could spend some time looking at the extinction time and things like that.
But that's not our main focus.
Yeah, that's not our main focus. So if you want to do
No
that,
problem.
that's fine, but I'm not terribly interested in that.
No problem, Professor. I will skip that. And but as a general trend, the higher the beta, the later it dies out. And
Hmm?
actually, F0 doesn't really change how sooner or later it dies out. So
Mm-hmm.
F0 doesn't counter, it's very, yeah, it's very
Counting.
counterintuitive. It's
Yeah.
very, very counterintuitive for some reason. Yeah. Yeah, it's very interesting, I think. But yeah, I won't spend too much time on it. So yeah,
So what are these tables that you're showing?
oh, that's just
Oh, it's
showing
just
when it
yeah, yeah,
dies
yeah, yeah.
out.
Okay.
Yeah, yeah,
Yeah, we
yeah.
could skip that.
And the table shows that a beta has a greater effect in impacting the die-out time than
Okay.
F0, which is counterintuitive. So yeah, and just want to show you that I actually keep all the data, like the original things here. So everything has a evidence to back it up. Just want
Okay.
to show you that. So we can include that maybe in the paper as our evidence or yeah.
Mhm.
Yeah, all right, that's my research so far, Professor.
Okay. This is a big improvement, Vincent. So that's very good. I'm happy that you have some solid results and you're kind of getting on track. Uh, there's a few things I'm gonna say and ask you. One thing I'm gonna ask you is to have regular meetings, not necessarily strict schedule, because I understand that both you and I could not always kind of commit to a specific time on weekly basis.
Hmm.
Our meetings should be arranged when you have some results. But what I'm asking for you is to kind of try to have regular meetings so there's not so much time going by and we need to kind of
Speed it
bring
up.
this project to a close and have you kind of finish the project and write a paper on it. So, just to be kind of concrete, let's aim for one meeting per 2 weeks.
No problem, Professor.
Is that fair?
Is that fair? That's really fair.
Okay.
Yeah,
So minimum, let's just say we might have like 2 meetings per week if you have a lot of results and you're working very hard and you
sure.
keep generating results and you want to talk to me. Sure, we can have more meetings than once every 2 weeks, but at the very, very basic, just like
Yeah.
minimal, one meeting every 2 weeks. So today is a Monday, but for both of us, it's a holiday. So, obviously I can't meet you on Mondays at noon because I have class then. But let's say 2 weeks from now, not the coming weekend, the next weekend, we have another meeting. And as time gets close, we can kind of fix that, whether it's a Saturday or Sunday, and whether it's noon or a little bit before or after that. So
Sounds good,
that's
Professor.
something we kind of settle. So at the very latest, I need to hear from you in like 10 or 11 days from now
No
in
problem.
order to schedule something for the upcoming weekend. And if you have something sooner, then you just email me and say, "Oh, I got results. We can meet next weekend." Okay,
Sounds good,
so let's
Professor.
keep that in mind. And then the next thing in terms of the research part is that I have asked you to kind of look into periodicity a little bit more carefully and find out exactly how you can characterize the period and oscillations. I've asked you to look at alpha in particular, but even beta that are smaller than 1%, to see the effect of those in your model. And I've asked you to concentrate on model A instead of model B because it doesn't seem to have a lot of interesting stuff coming out of model B. Okay?
Sounds good, Professor. I just want to clarify and make sure I get everything. So first, meeting regularly, and second, the the mission for next meeting is to look at when alpha starts and beta starts from dying out to the stable period and
Mhm.
how I can
Stable
accurately
stable state, not necessarily period, right? We
like
want
yeah
to,
yeah
so
yeah
first we want to have something that's not zero,
mm-hmm.
right?
Yeah yeah yeah
When that happens, and then next, after we find out where our transition to activity occurs, Then we want to have an understanding of what that activity is like, whether it's periodic, pure periodic, like sinusoidal, or is it kind of periodic plus a noise, or is it completely just chaotic and not any regularity to it? Does
So
that
you're
make
saying,
sense? Yes, go ahead.
but theoretically, doesn't it show a? So you're saying that it's probably not always true that. So you're saying that under some parameter, for example, alpha and beta are both really low, you might still enter a stable stage, but it might not necessarily enter a oscillatory stage. But for a good parameter, it enter the oscillatory stage after the stable stage.
Okay, so let me be kind of precise as I can be in terms of the possible behavior that one can imagine for this model, and then simulations need to bear this out. The first expectation is that if alpha and or beta are small enough, particularly alpha is small enough, then the system starts from some initial active state and will eventually die out. And the time it dies out, it is inversely proportional to alpha for small enough alpha. Okay.
Sounds good. Yeah, that's
Okay.
essentially what we're doing in Model 2, right? Kind of similar.
Well, kind of similar, but that happens for a low range of alpha in the first model. Yes.
Sounds good. Sounds good.
Okay. And it's inversely proportional to alpha. Okay. Meaning that the larger alpha is,
Yeah, yeah.
right. Okay. So that's one behavior. Then the next class of behavior is a state where the model remains active and self-sustained, meaning that it does not die out. Now, then the question becomes, what kind of activity do I have in this steady, stable state? And I can think about three possibilities. One possibility would be very nice sinusoidal oscillatory behavior, just going up and down very smoothly. That would be very amazing if you ever saw that. The other, so that's where you characterize the period, if that happens. Then the next behavior would be a noisy oscillation. So it won't be perfectly oscillatory. It would be going up and then coming down and going up and coming down and going up and coming down. So it would be an oscillation with some sort of noisy behavior. That's the second type of behavior. You can still pretty much define some sort of period for this behavior, although it's kind of noisy, but it's noisy within some oscillatory behavior. And then the third type of behavior is that it's just completely noisy. It's not, doesn't really have any oscillatory background. It just kind of goes up, stays up sometimes, comes back down, and then just, it's just chaos. There's no regularity to it. It's just noisy, steady, with no periodicity to it. These are the
Sounds good, Professor.
three peer behaviors of active states, and it would be very nice if you can kind of distinguish these three behaviors based on what the parameters of alpha and beta would be.
I'll find a way to get the result, Professor. So one
Okay?
last question. Do you want to change K and N?
Not for now. So your N is very good. 20,000 is good as long as you're getting quick results. We don't want to make that too much, so your run times would be very long. And your K of 200 out of 20,000 is also initially good. We might want to change those things later on, but for now, we want to kind of focus on what I just said.
Sounds good, Professor. Thank you so much. I'll send you the result as soon as I can by email. Maybe you
Awesome.
can take a look at the result report first. I'll explain everything, including the rules of the models and what my findings are and how I define those trends. And I'm looking forward to the next meeting. Thank you.
All right. Thank you so much, Vincent. Have a nice day.
You too. Yeah.